I want to discuss the marking schemes of a part of the exam taken last year in 2023. This is for electrical power systems and distribution. The parts about the transformers and per unit systems and fault analysis. There were some questions on the parts related to this per unit system. There was a question about a transformer with 500 MVA capacity, the ratio 10:1, and 220 kilovolt on the high tension side or primary side, and the leakage reactance or the series impedance of the transformer of 20%. In the first question, we're asked to obtain the actual impedance on the high tension side. We need to firstly calculate the base impedance, on the low tension side. We need to firstly calculate the Z base or base impedance on the low tension side. In general, impedance equals V squared divided by S. V on the low tension side is 22,000, because if this is the ratio of the transformer 10:1 and you say primary is 220 kilovolt, then the low tension side or secondary side is 20 kilovolt. It's 10 times less. So 22,000 squared divided by S, or apparent power, is 500 MVA. So that is 500 million volt ampere. This gives us 0.96, or if you want, you can type in this way: 22 squared times 10 to the power 6 over 500 times 10 to the power 6. This is clear, 10 to the power 6, because this is mega. And why is it 10 to the power 6? Because that is actually 10 to the power 3 for 1000, and then a square for this square in the formula. Once you've got this base impedance, you can multiply it by the per unit impedance to have the actual impedance on the low tension side, which is 0.212 ohm. Part B, or section 2, is the same question, but about the actual impedance on the high tension side. So again, you need to calculate the base impedance for the high tension side, which is V squared divided by S, 220,000, because that is 220 kilovolts square, divided by 500 MVA. And then obviously VHT, or impedance on the high tension side, is the per unit one, 20% with 0.22 times by this new base impedance on the high tension side. Section 3 says if the base power of this system changes to 100 MVA. So the transformer has its own capacity rating 500, but in my new system, I'm considering 100 MVA as the base power. And also the base voltage on the high tension side is going to be 110 kilovolt. You need this big formula for transformation from a given per unit to a new one. So a new per unit impedance equals a given impedance in per unit, obviously, multiplied by the new power divided by the old power, multiplied by the old or given voltage divided by the new voltage square. So you see the ratio of voltages is inverse of the ratio of power. And don't forget this square. So the given impedance is 0.22, because they say 22% of a leakage reactance. The new base power is 100, and the given base power is actually the rating capacity of the transformer, and that is 500 MVA. The base voltage in the old system, which is actually the base given voltage, is 220 kilovolt. And the new base voltage is 110. This is given here, 110 kilovolt square. So if you work out this one, you get 0.176 per unit. In the last section, they say, okay, in this new system with 110 kilovolt and 100 MVA, calculate the transformer impedance on the high tension side. So you see, in section 3, we obtained the new per unit. Now, it's like section 2 that we moved from a per unit to an actual impedance, but this time we need to use this new per unit and the new base voltage and base power. So firstly, obviously, we need to calculate the base impedance in the high tension side, V squared divided by S. V now is 110, not 220. Be careful, this is a common mistake here. 110 because we are in the new system. 110,000 because that is kilovolt square divided by the new power, not the initial capacity of the transformer, the new power, 100 MVA. This is for mega MVA. So this is going to be your new base impedance on the high tension side, 121 ohm. Now, the actual ohmic impedance on the high tension side equals the new per unit, which is 0.176, multiplied by the new base on the high tension side, 121, and you get 21.29 ohm. Just to verify if this is correct, this should be more or less the same as what you got in section 2, 21.2, and here 21.29. That is the difference is because we had some approximations in our calculations. Okay. Next question was about well, in that exam, we had also a part on a network with a configuration, but that had some descriptions and with some simple calculations. We had a lot of examples done in the class, so we skipped that one and we moved to this short circuit calculation. So the question about short circuit calculation had a circuit. You should be able to see it in the original paper. So again, that is the paper from the main exam taken in 2023, May 2023. So here we had a transformer, a B1. In the original one, you had only B1 transformer, a generator connected to this B2, two transmission lines, two transformers, and one more local generator. In the original question in the paper, they say the fault level at B1 is 450. And in the first question, they say the base power for this system should be 5 MVA. Now, in order to draw this reactance diagram, you need to look at the original circuit. And you see, we always start with a neutral node or a reference node on the top. Then we make this impedance or reactance in order to represent the fault level of the main bus bar. Then the transformer connecting B1 and B2. Then the generator connected to B2. It doesn't matter if that generator is drawn upside down or the other way. The only important thing is to look which side of the transformer is connected to which bus. We see G2 from one side is connected to B2 and from the other side is connected to N. It's not actually drawn in the single line diagram, but here in the reactance diagram you need to draw this one. Then from B2 to B3 there are two parallel transmission lines, and then B3 is connected to B4 via these two transformers and then circuit breakers, and then there is a local generator G1. From one side it is connected to B4, and from the other side it is connected to this reference node. The first item you should calculate is this reactance XS. XS, well, there is a proof we had in similar cases, and you may also see the proof here. But if you want to do it quickly, this XS equals the base power, okay, divided by the fault level of B1. So 5 MVA divided by 450. Okay, that's it. 5 divided by 450, and that is 0.011. If you want to know how this is the formula, you can look at this proof. Just to avoid confusing, I don't explain it now anymore. To see the other items now, this has been discussed in several cases. So let's move to the next item, which is the first transformer here. In the paper, this 0.1 is actually the given reactance. 20 MVA is the capacity of this transformer. So we multiply the given reactance by the new base power, 5, divided by the given power, 20 MVA. For the generator, if you look at the paper, you see the reactance of G2 is 0.17 or 17%. And the size of this generator, or the rating power of the generator, is 2.2 MVA, while the new power is 5. So 0.17 times the new power divided by the given power, 0.38 per unit. For the transmission lines, we need to calculate the base impedance. Then we multiply the given ohmic impedances by the base impedance, and this is done in the next slide or next page, so let's skip this one for now. For these transformers, the power or rating of these transformers are 5 MVA, the same as our common base power, so you don't have to do anything for these transformers. Well, for this local generator, again, the given power is 2.2, so that is different from my 5 MVA, so I need to change the per unit. The given per unit of this generator is 0.12 or 12%, which should multiply by the new power, 5 MVA, divided by the given power of the generator, or the rating of generator, 2.2 MVA. So you get 0.27 per unit. Now let's see how we calculated this per unit values of the transmission lines. So you know a base impedance equals V squared divided by S. Here the level of voltage of these transmission lines is 33 kilovolt. So the voltage is 33 kilovolt, 33 times 10 to the power 3 square. And power, you should use the common base power of the system, 5 MVA. So 5 megavolt ampere. So your base impedance for the transmission lines is 217.8 ohm. Now, for each of those components of the impedance, the resistance and the reactance, you just need to divide the ohmic value, or the given value, by this base value. 3 divided by 217.8 and or 9 divided by 217.8, and you get these values to be put in this diagram. Now we need to reduce this network. So if I go back to this one, you see here these two reactances are series. You can add them, and once you've done this, that reactance is parallel to this generator. These two are parallel as well. Obviously, you can remove the resistances because you're reducing this network for short circuit analysis. And these two. Well, you know, when two reactances or impedances are parallel and they have equal values, you can replace them by half of them. So if these two are 0.1, 0.1, you can replace them by a single reactance with 0.05 per unit. The same for these two reactances. So you put half of them. But here we need to firstly add 0.011 to 0.036, and that is 0.47. Then that 0.47 and this 0.38, they are parallel. You need to calculate them. Yeah, here. So you get 0.032. Then you add this to the other ones. This is the replacement of the transmission line, and this is the replacement of those two parallel transformers. And this is G1, that local generator connected to B4. Okay, then these three can be added together, which will be 0.102, and then these two are parallel, and finally you get 0.072. You don't have to show all of these steps, or you may want to show more steps, whichever is convenient for you. Sometimes you can do all your calculations on the same diagram, sometimes you need more iterations. All are okay, and you don't have to put J, but we should remember this is only reactance, this is only the imaginary part of the impedance. Well, that's enough for our short circuit calculation. So in section B, there are three configurations. The first configuration is when the circuit breaker 1 is open. So we have the main part. The main part, if you look at this reduced network, is this one. You see? So 0.102 is the impedance of the main part. So I only need this 0.102 in this formula. Don't forget to write this formula IF equals VF over ZF, because this shows you understood what you're doing to calculate symmetrical short circuit current. Okay, most of the time voltage is 1 per unit. ZF is what we saw from the main branch. So you get 9.8 per unit as the current. Section 2 or II in part B is when you have only local generator. There is an emergency and you have only the local generator. So that means circuit breaker 1 is closed while CB2, CB3, they're open. So you only have this G1. And if you look at the reduced version of this network, you need only this impedance, 0.27. 0.27. So IF equals 1 over J, 0.27 per unit, and that gives us negative J, 3.703 per unit as the short circuit current in per unit. And finally, in III, this system should be analyzed as a complete system. So all circuit breakers are closed. So we need to take this one, because this impedance was the equivalent reactance of the whole system, J.072. So J0.072, and you get 13.89 per unit. In part C, the question is, okay, in part B, you got all per unit currents for different configurations. Now calculate actual currents for each of those configurations. When you go to calculate actual current, you need to know base current. And once you've got base current, you can just multiply it by that per unit current. How to obtain base current? This is the formulation. I base equals S base divided by root 3 V base. S base is the one given in the problem, in the exam, in the question, 5 MVA. What is VB? You should look at that bus where fault occurs. Here, that is in B4, and the voltage is 11 kilovolts, so 11,000. Be careful, we had some exams in which the fault occurred in a low voltage bus. So that means it didn't have kilo, it was like volt, 415 volt. So not necessarily always you need to multiply by 10 to the power 3. Here we multiply by 1000 because this is kilovolt. And this is multiplied by 1 million because this is 5 MVA. Be careful with the scales of unit of measurements. So this is my base current in amp, and I just need to multiply this 3 times by each of those per unit currents I obtained in part B of this exam, of this question. Okay, so you get this actual currents, actual fault currents. In part D, they say, okay, for that bus bar, if the fault level is limited to 60 MVA, show that we cannot have all generators, all the system to be operating. We cannot have everything operating. So everything is in service, including G1 and this main stream. Then the fault current is 13.89, correct? Because this is the configuration in which you included all the components. So if 13.89 per unit is your short circuit per unit, this is equivalent to 69.45 MVA of fault level. Because when you go to calculate fault level, which is actually fault power, you need to multiply per unit fault by base power. Okay, per unit fault by base power. This is per unit fault, and you multiply it by base power, and you get here 69.47, which is obviously greater than 60 MVA, which is the limit of this. So this is the proof. This is easy. In some cases, you need additional steps. It depends how logically you interpret that statement in section D. Okay, for this statement given for section D, this proof is more than enough. Just a hint, last one. These per unit currents, although they are per unit currents, and obviously when you go to calculate actual current, you can multiply them by base current. At the same time, you can say they are also per unit fault level. When I say fault level, that means fault power, okay? So you can say they are also per unit fault power. Why? Because in this system, we assume voltage pre-fault equals 1 per unit. So in this case, current and power in per unit are the same. That's why when somewhere they are asking what is the actual fault level, which is actual fault power, you again take these per unit values and multiply them by base power, the same way you do for current, actual current. Okay, now we can have a quick look at all formulation, possibly all formulation, hopefully, you need for my part in the exam. This is what you need actually to obtain that series reactance representing the fault level of the main bus bar. You know, always when you draw the reactance diagram, firstly you need that reactance. You divide the base power, which is the common base power, by the fault level of that bus bar. This is X per unit, or XS we usually show. I base, when you need actual current, firstly you need base current. So base current equals S base divided by root 3 V base. Remember, for S and V, put in volt amp and volt, not mega or kilo, convert them. IF actual is I base multiplied by IF per unit. And fault level, the same IF per unit, you see, you get, but this time you multiply it by S base. Because IF equals SF per unit, because we say VF equals 1 per unit. In case you need base impedance, like for transmission lines, in the short circuit analysis question, or in transformer questions, that equals V base squared divided by S base. And this formula is when you transform an old per unit to a new one. The new per unit impedance equals the old per unit multiplied by the new common base power divided by the old power. This old power is actually the rating of the device, multiplied by the old voltage divided by the new voltage, the new base voltage, and square. Usually for the question about short circuit analysis, you don't need this term. This is enough. But sometimes for the question which is only about transformers, when we give you the leakage reactance and we say what is the actual reactance on the high tension side, low tension side, blah blah, you may need this one. In case in section 3, voltage, new voltage is different from the rating voltage of the transformer. Finally, per unit quantity equals the ohmic or actual quantity divided by the base quantity, and this is based on Ohm's law. IF equals VF over ZF. Okay, good luck in the exam, and thank you for watching.